Okay, we're going to take a look at Chapter 18, which is sampling distributions. We are going to be on Chapter 18 for a while because this is really laying the foundation for the entire rest of the course when we get into inference. So it's very important that we have an understanding of sampling distributions. We're going to be looking first at sampling distributions of sample proportions, and then we'll be looking later at sampling distributions of sample means. So suppose we want to know the proportion of adults in the United States who watch The Walking Dead. Side note, I don't watch this anymore. I used to like it at the very beginning, but then it just had too much drama in it. So suppose we wanted to know this information. Well, the true proportion that describes the population is called a parameter. And in statistics, the parameter is not known. If it was known, we wouldn't need statistics. So keep in mind the parameter is the true proportion of the population. You can also have parameters that are means, but we're looking at proportions right now. Since we don't know the parameter, we use sampling techniques to estimate the parameter. A statistic is a number that is calculated from sample data without making use of any unknown parameters. This statistic estimates the parameter. So in statistics, that's what we do. We take a sample, we gather a statistic, and we use that to estimate the parameter. So for example, a telemarketing firm in Columbus uses a device that dials residential telephone numbers in that city at random. Of the first 100 numbers dialed, 48% are unlisted. This is not surprising because 52% of all Columbus residential phones are unlisted. Identify each percent as a statistic or a parameter. You might want to pause for a minute and look that over. So the 48% would represent the statistic because that's talking about the sample of those 100 numbers. The 52% is what they're telling us is truly the unlisted numbers. That would be the parameter. Suppose that in fact 30% of the population of all adult U.S. residents watch The Walking Dead. Pretty sure that's not very accurate. Then the true value of the parameter we want to estimate is p equals 0.3. Of course, we would not sample if we already knew the true proportion was 0.3. We are doing this to see how sampling behaves. Okay, so we never really know the true parameter value, which again is why we use statistics. But in order to see how this works, we need to make that assumption. So what we could do is we could simulate taking a simple random sample using a table or a calculator. We could let 0, 1, and 2 represent watching The Walking Dead, and 3 through 9 not watching. By the way, what distribution does this have, if you think about that for a moment? We just got done talking about Bernoulli distributions. So there's only 2 outcomes. You either watch it or you don't, assuming that everyone is independent in our sample, and the probability if it were the same for each person. So we can see that. If you start at line 120 and you take a random sample of 20, and so if we look here, we've got 2, 2, 1, and 0. So those were representing watching Walking Dead. So you can see that we have 4 out of 20, which is 0.2. So our estimated proportion is 0.2. If we repeated another sample, would we get the same results? Well, of course not. We would expect not to get the same results. That's called sampling variability. The value of a statistic varies in repeated random sampling. So the procedure for estimating P, this is what you do. If you are trying to estimate the true population parameter, then for the proportions, then you take a large number of samples from the same population. You calculate the sample proportion p hat for each sample. You make a histogram of the values of p hat. And then you examine the distribution displayed in the histogram for overall pattern, center and spread, and outliers or other deviations. So for example, suppose we want to take a simple random sample of size 100 from the adult population. Further, suppose we want to repeat this 1,000 times. Now think what that means we're doing. Sample 100 people, get a p-hat value. Do it again with another 100 people, get a p-hat value. Do it again with another 100 people. Get a p-hat value and do this 1,000 times. We definitely don't want to use a random number table. It would take a long time. So I used a Minitab software, which was much simpler, just to show you the results. These are the results. So these are the results of 1,000 trials with sample size 100. Describe the center, shape, and spread. Are there any outliers? Well, hopefully what jumped out to you right away is that we see we have an approximately normal model. So with this normal model, notice where the center is. It appears to be about 0.3. And then if you were to look at the standard deviation, keep in mind that for a normal model, that we would expect to go maybe 3 standard deviations out to the very edge. So from 0.3 to 0.45 is a distance of 0.15. 0.15 divided by 3 is about 0.05. So we would expect, according to this approximately normal model, it appears that our mean is about 0.3 and our standard deviation is about 0.05. There's what it actually is, 0.30163, 0.04530. So you can see that was pretty close. So it appears to look approximately normal. The center appears to be about 0.3 or 0.31, and then you could identify the spread from 0.16 to 0.45, but it would be better to notice that the standard deviation was about 0.05, and there are no outliers. So suppose I alter my sampling, and this time we're going to take a simple random sample of size 2,500 and repeat the sample 1,000 times. So that would be like contacting 2,500 people, finding out if they watched The Walking Dead, coming up with a p-hat value. Then do another 2,500 people, get another p-hat value. Then do another 2,500 people, get another p-hat value, and do that 1,000 times, which is why we do simulation. Who would want to do that? That's a lot. I don't even think we have that many people that we would be able to ask. But here's the results. So if you were to describe the sampling distribution, the center, shape, spread, and outliers, notice it's still approximately normal. Notice the center appears to still be 0.3, but the most noticeable difference is the spread has changed. It's so much less. So we have so much less variation. It turns out to be about 0.009 for the standard deviation. So here the two distributions are side by side. This one is with a sample size of 100. This one is with a sample size of 2,500. Notice the p-hat value doesn't change much. It's pretty close to what we actually said it was. But look at the standard deviation. What a difference. Now here's the deal with sampling. You don't generally get 1,000 chances to come up with an estimate for the population proportion. Generally, you get one shot at it. You draw one sample, and you have to make some kind of an inference about what you think the true population proportion is. Well, if you only get one shot at it, and you take a sample size of 100, and maybe the sample that you get has a proportion, a sample proportion of 0.45, because you could have this one over here and get 0.45. And maybe you go to the television company, or you go to the people who are, if it's Law and Order, and you go to the people who are in charge of the advertising, and you say 45% of the population are watching this show. Well, they're going to charge really high prices for advertising if they have that many people viewing. Then if the advertising companies find out that really that wasn't accurate, you're going to get sued. And if you are the statistician, you're going to lose your job. Or on the other hand, maybe you tell the company, you know what, only 15% of the population is watching this show, but it's actually a higher value. It's actually 0.3. Well, then the advertising prices are going to be very low, and when your company finds out, you're going to get fired if you're the statistician. If you only get one shot at it, you want to make sure your sample is large enough so that if you're wrong, if you think that it's 0.32 and it's really 0.3, well, that's not much of a difference. So there's so much less variability here that we see that with a larger sample size, we get better, more consistent results. And that's what is key. We want consistency, and this is just way too variable. So we don't have the consistency that we would need. So when the sample size is increased, the mean stays approximately the same, but the spread is much less varied. Now I want to point out that I'm using the word mean, And you might look at that and say, wait a minute, I thought we were talking about proportions. We're actually talking about the mean. Whoops. Let me go back here. We're actually talking about the mean of the p-hat values, the mean of all the p-hats. So I'm finding all these p-hats and then I'm calculating a mean for those. So that's why I'm using the word mean instead of proportion, because we're getting all these p-hat values and then we are averaging those. So the other thing that we have to look at that is important is the bias of a statistic. And a statistic used to estimate a parameter is unbiased, which is what we want, if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So the goal of an archer is to hit the target. What does this have to do with statistics, you ask? Maybe you didn't ask, but I'm telling you anyway. We could have high bias, and in high bias, the sample proportion misses the parameter in the same direction each time. So it's missing in the same direction each time. But we also have low variability, and there's little spread in the sampling distribution of p-hat. So it's wrong, but it's consistently wrong. This can happen a lot of times when you have a poorly worded question that, that you could end up with high bias. Not a good situation. We don't really want this to happen. Another possibility is low bias, which means the mean of the sampling distribution hits the center of the target. So we never actually hit the center, but we're centered around it. But we have high variability. There's a lot of spread in the sampling distribution of p-hat. So that's kind of similar to what happened with our smaller sample size. We also can have high bias. The sample proportion misses the parameter in the same direction each time, and also high variability. There's a lot of spread in the sampling distribution of p-hat. So that's like bad and bad, the worst of both situations. Or we can have low bias, which means the mean of the sampling distribution hits the center of the target, and low variability, there is little spread in the sampling distribution of p-hat. So we hit the center of the target, we are accurate, we are consistent. That's what we like to have, and it makes us happy. So just some final notes. The spread of a sampling distribution is determined by the sampling design and the size of the sample. Larger samples give smaller spread. Definitely something key to remember. As long as the population is much larger than the sample, say at least 10 times as large, the spread of the sampling distribution is approximately the same for any population size. So that's going to be one of the things we're going to have to make sure that our sample does not exceed 10% of the population. That is going to help us deal with the issue of independence. A lot of times we don't have independent samples, so we have to make sure that we do not exceed that sample size. And we'll be talking about that more when I show you some examples.